Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're gonna talk about fixing global warming gradually, part 3. In this part, we're gonna focus on grid, and this is the reason why we have not already solved it. So let's dive deep into it. So what exactly is this quote-unquote grid? Now this is the puppy that allows us to consume energy and make energy and sell the energy. Everything about energy goes through the grid. So this is the whole point. Why? Because grid has this magical property where it's instantaneous, meaning you could be a aluminum mill and you're gonna consume GG amounts of power, let's say hundreds of megawatts of power. And yes, some of them do consume that kind of power, and you just turn on your load. Why the heck everybody does not go down instantaneously? Because you put so much load into it. Who is taking care of that? Grid is the one that is taking care of that. So grid is the reason why you do not have to tell someone where it's like, hey, we're gonna consume this much. Grid is like, I got this, I can take care of it. Passively they can take care of it. So, and it also allows us to have long range transmission, because back in the early days, as in like very early black and white era, people had this simple logic where they have power plant. This power plant is taking care of this place. This power plant, this place. Engineers inside these companies decided something bold, something bonkers, is that they're gonna connect all the grid, interlink them, and they talked to their quote-unquote managerial people, and they were like, no, and engineers were like, yes, and they're like, no, it's gonna explode, and it's like engineers did it quietly. I'm shocked how well engineers organized this, and they did it. Everything was fine, just fine. It's just like smooth sailing. Nobody even noticed it, and we never went back to the dumb design of having one area reliable on only on one power plant. So this allows us long range power transmission. And how the heck we have this magical property? Because of physical inertia. That's all this is. Whenever you see a giant ass power plant, what does it have? Generally, it has some sort of turbine. Whether that turbine is running on steam or water or nuclear energy does not matter. It has generally something that is big ass and is spinning fast. So in case of India, it could be spinning at, let's say, 1500 RPM. In case of America, because it does have 60 Hertz, it may be spinning a bit faster than that. So that's what these things are. So what do you have? You have something big, metallic, heavy, spinning at 1500 RPM. So something, let's say 10 tons to hundreds of tons is spinning at that pass. Then it's connected to generator. Generators have something known as rotor. What does rotor do? Rotate. What does that rotor has? Mass. Now, grand total, you could literally have hundreds of tons, and grand total, we are talking about grid. Everything is interconnected. So every spinning mass is acting as one big inertial wheel where it is there. What does that give you? That gives you the moment somebody puts giant ass load. Let's say a stadium just came online and there's a giant ass flood, like just like bang, and it puts so much load. What does that load translate to? That translates to that energy is coming from the transformer near them. That transformer is leaching that energy from the substation transformer, is leaching from there. That substation is leaching that energy from another transmission substation, it's leaching from that. That substation is leaching energy from its generator's transformer. Generator transformer, it's magnetically coupled. So far, everything is magnetically coupled. Then that magnetic couple goes to the final stage of generator's rotor. Now, rotor is not physically, but it is magnetically coupled. So you put that load, it slows down. Energy cannot be created nor destroyed. So energy has to be there in the rotation, but it's not there. You put so much load into it. Now, what does that mean? That simply means physics is there to help you. You have hundreds of tons spinning, it's not going to slow down. Physics does not allow it to go from 1500 RPM to 0. Like, it's not allowed. Laws of physics is like, nope. So what does this mean? This simply means there is a governor or computer system that's looking at turbine RPM, or like whole unit RPM basically, and it's looking at it. It's like, everything is fine, everything's dandy. It's like, 1500 is becoming 1499. 1498. Okay. 1497. Yeah, somebody is putting too much load into it. Please, steam, go YOLO on it. They increase the steam valve and everything comes back online. That time where, like, the frequency started to sag and your steam system to actually take care of it, that time comes from inertia. If you did not have inertia, yeah, boom, fuses will go boom. So that inertia is the only backbone that we have that takes care of the whole grid. That's why you can do that. And it also works in reverse. For example, let's say that aluminum mill, that's GG amounts of energy that it's consuming. It's like, okay, our work is here is done. They turn it off, bam. You have hundreds of megawatt going poof. Now you are overproducing. What would that mean? That simply means that magnetic coupling that was slowing it down, it's no longer slowing it down. It will speed up. But again, inertia works in both ways. Where it's like, hey, 1500 RPM, computer would be like, it's 1501 now. It's 1502. Is 1504. Okay, steam, please chill down. Just chill. Somebody is like reduce load. That's the whole point of inertia. That's why we have spinning mass. This is the backbone. Why these things work? Mass. That's why we have to thank those engineers who fought against the management. Da shall always destroy management. So physical inertia is the stabilizing factor. It's big, heavy, spinning mass that keeps us everything. Basically, it's acting as a giant dampener. That dampener is giving you time for your computer system to take care of it. So this is what we call grid. So what's the problem exactly? Well, problem exactly is that we never planned for renewable energy sector, so to say. So our plan was built on back in the old days. We had one power plant and consumer. We had producer, consumer, and everything was very organized, so to say. It's like we're gonna plant a giant as power plant here, and it's like we're gonna build the grid for it. Everything was designed in that way. But here's the renewables do not ask for your location. It's like I'm here whether you consume it or not. So you have to go where energy is available, but that case correct. The grid was not designed for that. So our grid was basically designed as a reverse engineer, so to say. So we built links. Let's say a link is built, awesome. That link gets saturated. Now we built another link. That links get saturated. We built another link. Everywhere is exactly the same. You go to UK, it's exactly the same. You go to America, it's exactly the same. All the links you see is built after they have saturated a core link. So this link is not basically prepaid; it's postpaid. Now, sometimes it has been done if they are building a giant new nuclear power plant or hydro dam. Of course, in that point in time, they will build a grid extension with it because they know like we're gonna add, let's say, 1 gigawatt of power here, so they're gonna be like built it. Renewables change that equation. How? Well, it could be anywhere. It could be like, why don't you think USA have covered this part? They do not have the luxury to sell electricity here. If somebody taken care of it, like there are very few population here, and it's not even agriculture land. It's just raw available desert. So why don't they cover it? It's like they cover it, they have to build the grid there. So it's becoming a chicken and egg scenario. And yes, it has happened even in this area. It looks dense. It's not that dense actually. So it has, people have been rejected a solar farm proposal simply because we get it. It's awesome. You're going to fund it on your own. It's not even government money. It's awesome. I respect you. We just don't have a link to absorb that kind of power. It happens everywhere, India, USA, UK, everywhere in this country, because our grid ecosystem, the mindset of the grid, it was basically, so to say, postpaid. It's like, oh, we saturated it, okay, now we build a new one. So that created a serious problem. And modern power generation is completely different because it could give, basically create an ecosystem of prosumers. For example, you and I now can have solar farms. Now imagine in like this area, let's say it has a lot of residentials, hundreds and thousands of residentials, all of them put solar farm. Literally this place will become a energy positive, surplus in afternoon peak time. Everybody else is going down, it will become peak time. At that point in time, they might simply cut the power. They had to do what we call curtailment because they do not have the system to sell that kind of energy back. So this is the core limitation of grid. This system was good, it's awesome, it's amazing. It's just that now we have outgrown it. So we need to build this preemptively. And we have to basically, in case of India, India needs a basically ring loop of HVDC and 2 links of it, one outside, one inside, and then some jumpers to make sure that one point failure does not happen. And otherwise, like right now, that's our main issue. We cannot just add wind farm, we cannot just add solar farm, even though solar farms in India makes a lot of sense. We cannot just do it. Even though we have area, we can't just do it. So, and same with USA and Australia also. This is another aspect, like why Australia does not have it. They don't have grid for it. Nobody designed the grid before the power supply. So that's a chicken and egg scenario. That's why we are so limited in terms of our renewable uptick, so to say. Everybody wants to do it because it's economically viable now, but nobody can do it because this puppy is the, holding back. So how we can solve it? Well, thankfully, some technologies have reached maturity, and this whole series I'm focusing on things that you can actually do, a country can actually do, a community can actually employ. So HVDC. Now, thankfully, HVDC solves one of the biggest issue of transmission. We can't actually send AC for very far. Like, for example, China has this big ass dam, that is Three Gorges Dam, and that puppy generates 12 gigawatts. That's a lot of power, but they have to consume it 3,000 kilometers away. If they send that much power through AC line, yeah, nope. That power will be nope. Nothing, zero, nothing. Nothing is going to go on the other side. Why? Capacitance loss. So that's why you will always hear this sort of thing saying it has 50% less stress. But that 50% looks odd. It's like, are we wasting 50% of AC power? No. What does it mean? Simply, basically, instead of having 6% loss, you're going to have 3% loss per 1,000 kilometers. So that is the reason why you can actually have HVDC link that goes very far. Like you can truly have HVDC link around the globe also if you want to. AC cannot go that far, DC can. Then It also unlocks ability of cost-effective undersea cable. Be mindful. Can you bury a AC cable? Absolutely. Should you bury a AC cable? Hell no. So if you have like this sort of European Union kind of scenario, and you're like, hey, we're gonna jump the sea here. Yeah, no, just no. If you did that with AC, and let's say the salty water length is more than 80 kilometer, God help you. God help you. The power sent, it would be zero. It's like, we are sending gigawatts of power. Outside on the other end, it's like, sir, our meter is not spinning. We're not getting any power. 80 kilometer. Of course, it's not exactly 80 kilometer. You get the point. Like, it's not a good idea. But if you have to increase, let's say you're connecting two islands, God help you. In those sort of HVDC is like, I got you back. It's an ancient technology, surprisingly so. Like in World War II, Germans were building this. It's like ancient technology. So it makes cost-effective undersea cable, and it only needs two cable or even one. You can have monopole, you can have bipolar, basically plus and minus, or you can just monopole it if you really want to save money on cable cost. It does not need three cables. So that's there. And it also utilizes those cable far more effectively. Why? It does not have what we call a skin effect, meaning if you have ever paid attention to giant ass transmission tower, it will always have multiple thin wires rather than one thick one. Now we know how to make one thick wire. That's how stay cable bridge works. So why don't we use that? AC will not travel on it. AC is like, nope, I will not travel on it. So you have a thick cable like this. You calculate it based on conduction of copper. Let's say you calculate it. It's like this much. I'm gonna send this much amp through it. It should be able to handle it. If you send AC through it, it's like, nope, it's gonna melt. It's like, why? Because only the outside skin is conducting. Why? Because magnetic flux is changing. You have, in case of USA, 60 times on off, on off, on off. In case of India, 50 times on off, on off, on off. It's creating a skin effect in the skin itself. It's basically a sort of eddy current. It's pushing electrons out. So core is completely useless. And you can see that in modern basically AC lines, the core of those cables that you see, it's carbon fiber. They're not even putting conductor in there. It's like, it does not make any sense. It's not used. Putting carbon fiber allows them to increase the span length. So grand total, they reduce the number of poles. So that's another aspect. So even if I give you exactly the same link pole, exactly the same voltage, if I just change the on both ends, basically substations became, instead of AC substation, DC substation, using the same link, you can send more power because it has no skin effect, it has less loss, and it has no distance limitation. Now, that creates an issue. Like India has some really amazing system, China has some huge ones, India has amazing ones simply because we have a tri-link system. What does that mean? That simply means we have A, B, and C. Most of the HVDC right now that you see active in the world, that is just A to B. India has A, B, C, Agra East Corridor. And it's also big, some serious power. What kind of power? 8 gigawatt kind of big power. So we are talking some big daddy power here. And there's all other links also. It's not just one or two, there are many other links also. Now, this must have triggered a red alert in you. If you have a converter, how the heck you are magnetically coupling it? Because in our grid design, everything is magnetically coupled. You do not even have to think about it. You go to transformer magnetically couples it. Everything gets magnetically coupled to the generator rotation mass. How the heck you do it here? Well, engineers had this issue and they were like, okay, we're going to build a time machine and we're going to go to 1970 and they pull back this puppy. This puppy is what we call synchronous condenser. Now, go back to the old days where capacitors were not actually reliable. So how do you run basically a giant steel mill where you could have something that is brutal in terms of what you call power factor? How do you correct the power factor in those sort of era? Somebody came up with the idea, just build a giant ass motor, AC synchronous motor, and change the rotor current based on your load. You need something that has a variability. So you have a load and no load put onto motor. Motor is just acting as a passive system. Of course, it will waste some energy. It will act as some compensation. So there will be some wastage, but very minimal. And the rotor is just spinning. And you are changing the voltage that is going into the rotor part based on what is the power factor correction you need. Now, same thing is now Control C, Control V into HVDC stations. And this is providing two main things. First, actual spinning mass inertia. That's there, that's good. This allows them enough oomph time where they can be like, okay, somebody is actually putting some serious load, they can call back to a power station. And of course, nowadays we have optical fiber communication between power plants. They can easily take care of it. And this physically has giant enough inertia where it's like, I got this, I got this. So that takes care of it, and because it's a physically spinning mass, it takes care of all the three-phase angle. So you do not have to worry about like the phase angles are drifting and all that. Like imagine it this way, like you have one 120, one 120, one 120. Everything is awesome. But what if two of them started to drift closer? It will physically be impossible if this puppy is there. It will blow up the substation before that can be done. So that's why we use this puppy nowadays in HVDC link houses to stabilize everything. Be mindful, not necessary if your majority of the grid is still what we call AC, and it's like that is there already, you may be like, not necessary. But if you're like, I'm going all in on HVDC, yeah, you need this. So this is how we can actually allow hundreds of power transmission to go hundreds and thousands of kilometers without any issue over the whole planet if you need to. So HVDC is the first line. Then what about these transmission towers? So again, that's just a station part. Okay, you've taken care of that. What about the transmission? We have to use new designs of link. The older design, especially that system that you used to see, like that looks like a basically poor man's Eiffel Tower. Yeah, that's not gonna go. We have to use something better. Thankfully, new development have happened. That is gas insulated transmission line. It takes up exponentially less space, and you can bury it quite effectively, cost effectively also. So this is also China's. They have a small tunnel. In that tunnel, they have a small meter gauge, if I'm not mistaken, meter gauge or even a smaller railway gauge for customer. And they have 3 lines, 3-phase AC line. And it does allow you to bury AC lines with a bit less loss. If you had directly AC line and basically insulator and the soil, it's not very well insulated. Here, AC lines is inside that. There is gas insulation, and then there is this volume. So it has much lower capacitance. Again, you can take the same connection principle, apply it to HVDC, you are going to get more power, or you can use AC if you want to use AC, because again, HVDC converter station is not something that you want to put on every place. It's like, yeah, some big daddy power, some A and B, some strong powers, it will generally make sense for gigawatt scale. For megawatt scale, it's not really that viable. Again, it can be done, and there are some companies that have successfully reduced the cost so much that they have, like, smallest unit I have seen is 30 megawatt. It can be done if you need to. So we have gas insulated transmission line that takes up much more less space, and it can be buried safely. So you do not have to like, oh, the whole countryside is covered by high voltage cable lines. That is a taken care of part. Monopole transmission line like this puppy. This is the Indian puppy. I like that design. So this also reduces the footprint that is in the ground and also the volume print. For example, utilizing this technology, now you can send very high power cable lines, high voltage cable lines through a city using just a 3-lane road. Not 3 lane, as in like 6 lane total lane. Basically, you have 3 up, 3 down. So in the center part, you can literally have this puppy without touching any of the building, without having any clearance issue. I have seen this in Kanpur. There was not this pole, this design basically from back area, from like industrial area. There was power line coming on the old scaffolding design, and then this jumped into this monopole, and it was very slim. Same voltage, same capacity, very slim. So this also reduces the clutter that people have to deal with. Underground HVDC line, that's the easiest thing, because again, it also survives under sea and you do not have to worry too much. Be mindful, HVDC insulation is expensive. That's why sometimes people may prefer gas insulated rather than proper HVDC. But if you need to, or you can afford to, go HVDC. That's the best option you have. And there are new design competition. I'm not even joking that UK actually did design competition where they designed a new variant of this, which looks cool simply because they knew for a fact that they're gonna build more lines. If it's ugly, it will look ugly. So what if we work to make sure that it does not look ugly? It's kind of interesting design. Again, British people, they may have a different sense of art, so they may find it interesting. I would urge you to look it up. So that's how we can take care of transmission without covering the whole goddamn planet and skin surface of the planet into like electrical wires. Then we come to the distribution part. You generate like transmission requires main link in substation. Substation is the puppy that makes power actually usable, because they will take very high voltage of transmission line, drop it down to gentle levels of 33 kV. That 33 kV will go to the nearest substation, and then substation will send it to your pole mounted station. That pole mounted station generally will drop from 11 kV to 220 volt in case of India. So that substation consumes a lot of surface area, like physically huge. And if you have multiple links, you have to have that kind of area. There can be a size of a school building. I'm not joking, they're a huge puppy. Most times we generally see small substation, we do not truly comprehend how huge these things can get. And if you're talking about gigawatts, more gigawatts, it can become bonkersly huge. So more megawatts you add, the more you're like, hey, we are running out of surface area. So how can we reduce it? Thankfully, we have this puppy, GIS, gas insulated switchyard. I do not know why I call it switchyard instead of substation, but the logic is, the reason why substations are huge is because each cable has a imaginary sphere around it, pipe around it, so to say. That pipe is basically where electricity will jump if there is another conductor. So if you have 100 kV, you can be this far apart. If you have 33 kV, as in like 11 kV, 33 kV, 100 kV, so you need to have that kind of gap. So everything is about the gap. But if you have gas insulation, it has much more stronger insulation property. So now you can have two conductors that could be carrying as high as 500 kV very close to each other. So now you can truly compact everything. So this building that I was talking about, the amazing pole, this building is this thing vertical. So somebody designed a system where you can have even smaller footprint. And now we come to an interesting aspect where what is the two primary jobs of a substation? First is stepping it down. It makes sense, right? You can have 500 kV coming in, you have to make sure you are sending out 100 kV again for another substation. So that's stepping down, that's transformer. Look around the substation, you will find transformer itself is not consuming that much surface area. The surface area is primarily consumed by the metering stage and of course circuit breaker. So why the metering stage is so huge? Because it has two transformers, which we call current transformers and potential transformers, as in voltage transformers. So these two things, they literally are what they are. They allow you to measure current and voltage reliably, but they are huge, they are expensive. Now, and again, the expensive part is not that valid, but they do consume space. Square meter area, they consume a lot, and the bigger the voltage that goes, those also become exponentially larger. So in a small system, yeah, it's this big. In large one, it's exponentially larger. So like transformer is there. So what is from here to there, from bus bar to that? Yeah, is the systems. Basically, you will have circuit breaker, you will have isolator, and you will have current transformer and voltage transformer. Have we made any progress here? Yes, we have what we call these puppies. It can be integrated with this also. So this is what we call optical systems. Now utilizing optical fiber, we can sense magnetic fields with surprisingly high accuracy. So now you can sense voltage and amps without surface area cost, meaning you can literally, if you want to, you can put it on both sides of transformer if you want to. Like it can be done now. Of course, they are expensive, but more and more consumption will lead to more and more production. More and more production will cause cost to come down. And be mindful, many companies are already investing into this simply because it reduces the oil content. Every substation has giant amount of oil. And one oil content that you can't do anything about is transformer. But if your CT no longer needs oil, if your PT no longer needs oil, that's oil saving. That's awesome. Meaning how many places can go boosh, goes down. That's awesome. Increasing resolution. And be mindful, these things do not reach saturation. They do not give a damn. They are like, you put it, you forget it. They do not get interference by lightning. They do not give a damn about anything else. So they're like, shut up, take money. People are investing more and more into it. That allows this puppy to get even more compact. So the main benefit of using all this technology in together basically is gives you more megawatts with less square kilometer area wasted on just like, why that city's land cost is high? Yeah, because it's surrounded by giant buildings that are substation. No, it's like, and be mindful, you may have noticed this nowadays that there are cities that are, especially they are building new system. With this, they may have a substation that you have walked by and you would not have noticed it because these are so compact comparatively speaking. And be mindful, some engineers are working on warm temperature superconductor transformer. The reason for that is transformer, especially at large scale, as in like gigawatt scale, they waste like 1 to 2%. 1 to 2% of gigawatt continuously being wasted, that's a lot of unit that you are just like, poof. If you put basically superconductor there, its heat load goes to zero per superconductor, and all you have to do is passively insulate it. And of course, we'll have some nitrogen refilling into it. But overall, it could save enough money where people could justify buying a super expensive transformer. And be mindful, that will be even more small. So now you can have a small building that's like, yeah, what is this building? Which has like armored, walls around it, so it can withstand a missile fire. It's like, yeah, it's a 10 gigawatt substation. It can be done. Physics does not stop it. But it does require that substation to run on superconductor transformer, because right now we cannot shrink transformer that much. So this is the gas insulator. This all three tools that I have talked about allows you to take care of the grid part of our ecosystem. So this was my presentation on basically the part 3 of how to take care of global warming, and this will allow us to have a better grid that can actually absorb renewable energy. Right now we cannot absorb renewable energy. You would be shocked, I guarantee it, how many plants have been cancelled simply because we did not have grid connection there. So hopefully you have liked this presentation. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.